Hello. Today's lecture is about uniform circular motion. You may recall in geometry, if you have a circle and if you want to measure the arc length, which is the length of the arc, let's say that the arc starts from here until here, and this is, say, the radius of the circle. This is the center. That's the radius. And this is the arc length S. And this is the angular displacement theta. The relationship between those three variables is S equals R theta, right? R here, of course, is the radius of the circle, and the radius here is constant because it's a circle. But theta is a variable and S is a variable. The larger the S, the larger the arc length, the greater the angle, and so on, right? So now if I take the derivative of both sides, so I'm going to get something like this. S dot, the time derivative that is, S dot equal to R theta dot, okay? The dot here means the time derivative. It means ds dt equals R d theta dt. What that means is that suppose you have, let me go back to the circle. Suppose you have an object situated here at, say, t equals 0, and this object is moving, okay? And this object is moving until it arrives at this point right here at some later time t, okay? Whatever it is, t1, t2, whatever it is. And so if I want to measure the speed of the object as it goes around the circle like this, okay, which is ds dt, that's the speed of the object or the velocity of the object, is equal to the radius of the object times the time rate of change of theta, which is d theta dt, and we refer to this as the angular velocity omega. Okay, so omega is the d theta dt, or the change of the angle or the angular displacement with respect to time, okay? So omega is angular velocity. I forgot to mention that, keep in mind, when you use this relationship, an important condition to this relationship is that theta must be in radian, right? Radians. So in this case, the angular velocity unit here, the unit of the angular velocity would be what? D theta dt, and that makes it what? The unit here would be radians per second, right? That's the unit of it, okay? And the velocity here, or the speed here, is the tangential velocity or translational velocity, and the unit of it. So this is tangential velocity. The reason we call it tangential velocity, because notice that as the object is moving here, is moving in the direction of the tangent line, or the tangent vector, if you will. Okay, so we call it tangential velocity or translational velocity. Translational. I'll tell you in a minute what that means. Velocity. So it's a regular velocity where the unit of it is meters per second. You got that? Okay. All right. So we come up with this relationship that is a very important relationship in physics, where it says that the translational velocity, v, is equal to the radius multiplied by the angular velocity. All right? What does that mean? Well, think about it in terms of, let's say, the car. Okay, so you have a car, and here is a car wheel. All right, and the car wheel, let's say the car is moving in this direction. All right, so the wheel is spinning in this direction. The four wheels. Okay, that spin is what we could refer to as a spin. It's basically omega. Okay, omega is the angular velocity, is the velocity in rotational way, all right? And suppose that the radius of the wheel is r. As you know, the faster the wheel spins, the faster the car will move forward, v. You see what I'm saying? So there is a relationship between the forward motion of the car versus the rotational motion of the wheel. Similarly, say for a bicycle. So we have a bicycle wheel, and these are the spokes. And the bicycle wheel spins, so there is the radius of the wheel, r, and the spin here, omega, and then we have the velocity, the forward velocity of the bicycle as a whole. How the two are related? V equals r omega. Very, very important relationship to keep in mind. You got it? So here in this, so far, we have actually derived it from a famous formula that you know since you were a child, from geometry, S equals r theta. By taking the derivative of it, you will arrive at the relationship between translational velocity of the object and the angular velocity of the object. Okay? Another relationship that I want to cover, I'll be covering a certain relationship before we begin solving problems, and that is the frequency. Sorry. As most of you know, the frequency means the number of revolutions per second or per unit time. So the number of revolutions or cycles, if you will, cycles per unit time. And I'm going to say per second, per unit time, or second. Mostly we use second for the time, as you know. Okay. So imagine something that is spinning. For example, say go back to the wheel of the car or a bicycle, and it's spinning. If I ask a question, how many revolutions it's making in 1 second, that will be the frequency. I can say how many revolutions it's making in 1 minute. That will be an RPM, right? RPM, revolution per minute. That's also frequency. Okay. The reciprocal or the opposite of frequency is period. The period is the time it takes to make 1 revolution. You see what I'm saying? See, the frequency is how many revolutions per second. The period, how long it takes to complete 1 revolution. You get that? So the period here is the number, the time, or the time it takes to complete 1 revolution, or 1 cycle, if you will. Okay? And they are reciprocal of each other. If I designate the period to be the Greek letter tau, and the frequency the letter f, and the way and the relationship between them, basically the reciprocal of each other. So tau is equal to 1 over f, or f equals 1 over tau. Okay? So that's another relationship that you want to keep in mind between the different the relationship between period and frequency. Another relationship, now, I mean, we covered V equals R omega right here, and then there is also a relationship that links the angular velocity with the frequency. Please go back to your book and read about them. And the relationship here is omega is equal to 2 pi f, or omega equals 2 pi over tau. Okay? Let me go to the book, and I will let me solve one problem for you and show you how to use some of these relationships that we have just covered. Let me do, maybe I have a couple of examples to do. I'll start with this one. This one says a 4 centimeter diameter crankshaft turns at 2,400 RPM. Now, when we say RPM is the revolution per minute, what is that? Well, you can think of it as the frequency, but in minutes. Remember, when we talk about frequency, we say revolution per second. And by the way, it has a unit called hertz specifically for that. Revolution per second means is also hertz. So this is also frequency, but it's in the wrong unit. Keep that in mind. When we talk about frequency, it's always per second, not per minute. So you must convert to second. All right. So he says you have a crankshaft, diameter 4 centimeters. It is spinning or turning at a rate of 2,400 RPM, revolution per minute. Now he's asking, what is the speed at a point on the surface of the crankshaft? So basically, given the frequency, okay, what is the speed, V, okay? So we want to see a relationship between them. All right. So how do we solve this problem? Let me leave it on the side here. So I'm going to write down what's given to us, first of all. So we have the diameter, 2r, I like to call it 2r, is 4 centimeters. So that makes it 0.0, sorry. I want to make it, I'm a little bit ahead of myself. So that makes it, the radius is 0.02 meters, correct? There we go. And also given to us that the frequency is 2,400 rev per min, right? He said RPM, look at that. So I need to convert that to second immediately. So that's 2,400 rev per min is 60 seconds. So that makes it, so I'm going to use my calculator to calculate that. I'm sure you can do this in your head, but I'm going to use the calculator anyway. Divided by 60, and that will be equal to 40. 40 what? 40 rev per sec. And this rev per sec we refer to as the hertz. So that's 40 hertz, Hz. Okay? So we are given that. And now he's asking the question, what is the speed, the corresponding speed? You get that? He said, what is the speed of that thing? So how do we do it? Well, there are several ways of doing it. One way of doing it is we know that the speed is equal to omega r. Or for our case, the r is the big R, so I'm just going to call it big R here. So omega r. R is given to us right there, and I just need to find omega. Well, what is omega? Omega, go back to the note here, omega is equal to 2 pi f or 2 pi over tau. We have f already, we found it, so I'm going to use this one to find omega. So here omega is 2 pi f. So that will be 2 pi times f is 40 hertz, right? And that will give me, I just want to get a number out of that. So that will be 40 divided by 6.28. Answer is 251. 251.2 radians per second. Okay. And then he says, what is the speed, the velocity? So that is the velocity right here. So the velocity is omega r. So it is 251.2 radians per second times the radius is right there, guys, 0.02 meters. And then we multiply this by 0.02. And the answer is roughly about 5. So 5 meters per second. And there we go. I got the velocity. Okay. Okay. There is another way of doing it. Let me show you. So that would be basically a correct solution. There is another way of doing it. Think of it this way. So here is the crankshaft. Let's just symbolize it as a circle. Here's a crankshaft. And so you have this dot. Suppose that I tag one dot on the crankshaft. And the crankshaft, of course, is moving, let's say, in this direction. That's omega. So it's going this way, right? And it's making 2,400 RPM, right? It's spinning really fast, 2,400 RPM. So it's making a circle. So this is the radius r. It's making a circle of circumference 2 pi r like that. Okay, so if I want to calculate the velocity in simple terms, okay, let's say that I don't know any physics, I just want to use my common sense. Well, I know that the velocity is distance over time. See what I'm saying? So the distance traveled by this dot right here is basically the circumference of the circle divided by the time, or the time it takes to complete that cycle, which is basically the period. So one way to think about it is that the velocity is 2 pi r over tau. And that's actually a very famous formula that you can actually, keep in mind. And that's, I think, the solution that he used. Right there. See that? So we can do that. Let me show you how that would work. So I have given the RPM level, which is, he said, 2,400, and we converted it into the proper unit, hertz, so I have 40. So what I want to do, I'm going to get tau. So how do I get tau? Well, tau, as you know, tau is the reciprocal of the frequency, so that's 1 over 40, right? So that would be 1 over 40, so that's 1 divided by 40. Oops. 1 divided by 40. Answer 0.025 second. There we go. So I got tau. And so I can just plug in all of that in there. So I have V equals to 2 pi. The radius is 0.02, if you remember, divided by 0.025. And technically, we should get the same answer. So let's do that. So I have 0.02 times 6.28 divided by 0.025. And the answer is 5 as well. Okay, good. Another example, 4.4. Let me go to it. This is 4.4. Actually, it's example 411. Here it is. It says a small steel roulette ball rolls CCW counterclockwise around the inside of a 30 centimeter diameter roulette wheel. The ball completes 2 revolutions in 1.2 seconds. So what is that 2 revolution per 1.2 second? We can think of it as a frequency. Again, we want it in hertz. So anyway, so we can think of it as frequency. And now the question is, what is the ball's angular velocity, which means omega, and what is the ball's position at the second when theta is equal to 0? All right, let's see how we do this one. So here we have so again, always write down what's given. So we have a steel ball counterclockwise. Probably this is not important for now. And the inside of a 30 centimeter diameter roulette wheel. So the radius in this case is going to be 15 centimeter or 0.15 meters. So that's the radius. And then he said the ball completes 2 revolutions in 1.2 seconds. So I'm just going to go directly to the frequency. I know that the frequency is what? Number of revolution per unit time. So that will be, I forgot what the number is, sorry. 2 revolution per, so that's going to be 2 rev per 1.2 second. You see that? But my unit has to be at what? Revolution per second. So I can simply divide 2 by 1.2, right? So I have 2 divided by 1.2, and the answer is 1.67. So it is 1.67 rev per second, or I can say 1.67 hertz. You see what I'm saying? 1.67. Oops, I keep pushing the erase button. Hertz. There we go. Okay. Now he's asking the question, what is omega? Angular velocity. Okay. So omega, as you know, there is a relationship between omega and f, and that is omega is equal to 2 pi f. Simple. So all you need to do is 2 pi times 1.67, and then we just calculate that times 6.28, and the answer is 10.47 roughly radians per second, right? Okay, and part B, he says, what's the ball position? And basically he's asking for theta on the second, okay? The ball's position on the second. Okay, so how do we do this one? Well, I'm a little bit ahead of, I haven't talked about that, but we have something called rotational kinematic. I'll talk about it in a minute. And basically, remember the kinematic equation V equals V naught plus AT. So if you let V to be omega and A to be alpha, so we will have alpha for angular velocity. So it becomes omega equals omega naught plus alpha t. Okay. Another one is, again, I will come back to all of this in a minute. There is another one that relates the angular displacement. See, let me explain it. So I have omega is equal to d theta dt. If I multiply dt on the other side, so it becomes d theta equals omega dt. If I would integrate both sides like that, so I'm going to get theta equals, of course, the integration of omega, that would be, omega t. The omega here is a constant, so it would be omega t plus integration constant. We're going to call it omega naught. Okay. Theta naught. If we suppose, he says here in the problem that suppose theta initial, the naught is 0. So in this case, we have this relationship. Theta equals omega t. Another easy way to see it is this one. If you look at that, it says omega equals theta over t. Okay, which basically that. Okay. Anyway, so we have that, and he said, so what is the angular, what's the angle of displacement after on the second? Well, omega for us is a constant, and it's equal to 10.47. So I have here 10.47 radians per second times the time, he said 2 seconds. And when I do that, and that will give me 20.9, roughly 21. What did he get? 21 or 20? Yeah, 20.9. That's what I got, 20.9. So we have here theta is equal to 20.93 radians. And there we go. Okay. And I hope you know how to convert radian into degrees if he asks you for what is that in degrees. Okay. Okay. Here is another example. Imagine you have a CD, okay? A CD, radius of the CD is 6 centimeters. I'm copying this from my notes. And the CD's frequency rather is 7,200 revolutions per minute, okay? So that's basically the RPM of the CD. It spins at a rate of 7,200 revolutions per minute. And there are two questions here. The first one, what is the angular velocity of that CD? What is the angular velocity of this CD at t equals 4 seconds? Okay, in other words, if it starts from rest, what is the angular velocity of the CD on the 4th second? Also, the time it takes to make 90-degree angle. Okay? So in other words, here's the CD. Okay? And let's say I'm tagging this point. Now the CD starts to spin. The spin rate is 7,200 RPM right there. So how long it will take at this point to go from here all the way to here by 90 degrees, instead of saying? So if it's spinning in this direction to here, okay, it's 90 degrees. Okay. So how do we do this problem? Simple. So we know that omega is equal to 2 pi f. I need to find the frequency. Again, you want to find the frequency. The proper unit have to be in hertz. So that's 7,200 revolution per 60 second. And I can get that quickly. So I have here 7,200 divided by 60. And that will be equal to 120 hertz. Okay? That's the frequency. Now, the second step is omega is 2 pi f. So that will be 2 pi times 120. So the angular velocity is equal to 753.6 radians per second. There we go. Okay. Now, he's asking the question, what is omega on the 4th second? Okay. So in this case, I need to find alpha. In other words, because here what you have the CD starting from rest. Okay, it starts from rest and then it starts spinning. Eventually, it reaches, RPM of 7,200. Okay, so on the 4th second, so that means it starts accelerating. Okay, I'm going to do this problem later on when I cover rotational kinematics, this part. But let me calculate how long it will take the CD to go to travel or to make 90-degree angle. Okay, with such RPM, you see what I'm saying? Okay, so how do we do it? Well, it's similar. The reason I picked this example is because it's similar to the previous example here, where we said that theta is equal to omega t, or it comes out from here, omega equal theta over t, or delta theta over delta t. So let me see that. Let me see how it works. So basically, we can say that omega is delta theta over delta t. And of course here, remember, theta is always in radian. So we have theta is 90 degrees. I need to convert it to radian, so that will make it pi over 2. I hope you know how to do that. And that's equal to 1.57 radians. Okay, so 1.57 it corresponds to 90-degree angle. Got it? Okay, so he's asking for how long, the time it takes. See that? So I am going to come to this formula and solve for t. So delta t is equal to delta theta over omega. And I have already calculated omega right here. And delta theta is this one right here, 1.57. Remember, delta theta means theta final minus theta initial. Initial theta is 0, so that's just theta final minus theta initial, minus 0. And that will be just theta, which is this one right here. See what I'm saying? So that will be equal to theta over omega, and that's equal to 1.57 divided by 753.6. And then we can calculate the time, and that will give us 2.08 times 10 to the negative 3 second, or roughly 2.1 millisecond. Got it? Okay. So let me jump now to rotational kinematics, and you know what? Let me try and do this problem. This second part here. It said, what is omega after the 4th second. Let me see if I use our common sense before we do the rotational kinematics. Go back to, when we studied kinematics. We said that we defined the acceleration to be, if you remember, dv dt, or delta v over delta t, correct? Now, what corresponds to that is alpha equals delta omega over delta t. That's the meaning of it, okay? So, as I explained it earlier, we need to, so we have a CD starting from rest, okay? And then start accelerating. So what is the speed of it after 4 seconds, okay? So we need to know the rate of acceleration, alpha, this one, angular acceleration. That's what I'm trying to say. So, given to us that after 4 seconds, this is given to us. I mean, this RPM is after 4 seconds. So that means after 4 seconds, omega is equal to this number. So after 4 seconds, given to us, after 4 seconds, F is equal to 7,200 RPM, which we converted to hertz, or we can say omega is equal to 753.6 radians per second. So we can simply use this formula and say that alpha is equal to omega over time. So that will be 753.6 divided by 4 seconds, and this will give us the angular acceleration. We can calculate that, and that will give me 188.4 radians per second squared. Okay? Okay, good. So let me move on to the next topic, and that is rotational kinematics. You will understand rotational kinematics if you understand kinematics, the equation of kinematics, the one we covered back in, I think, lecture 2. And if you remember the kinematic equations, translational, what we call translational kinematics, are given by the following 3 formulas that I hope that you already memorized. V equals V naught plus AT, V squared equals V naught squared plus 2AX, and X equals V naught T plus 1/2 AT squared. Okay? Now, if I would, let me just box them like this. Remember, this is translational kinematics, which means motion in straight line. You got that? This is what we've been studying. Right now, we are studying motion in a circular way, okay? Rotational. So what corresponds to V is omega, and what corresponds to let me put it in order. What corresponds to displacement is angular displacement. What corresponds to acceleration is angular acceleration, and of course time is time. Okay, so let me repeat it. What corresponds to linear velocity or translational velocity is omega, angular velocity. What corresponds to linear displacement is angular displacement. Tangential acceleration or acceleration is angular acceleration, and then time is time. So what I'm going to do now, I can simply look at those and replace V here with omega, replace A with alpha, T is T, and replace X with theta, and I will get rotational kinematics. Let me write it down here. It's really that simple. So in other words, if you memorize translational kinematics, it will be easy to to write down rotational kinematics by memory. So you have omega equals omega naught plus alpha t. Omega squared equals omega naught squared plus 2 alpha theta. And theta equals omega naught t plus 1/2 alpha t squared. And there they are, okay? These are what we call the rotational kinematics. All right? Good. Let me give you an example and show you how they apply. Suppose you have a particle that moves in a circular path, and suppose that the initial angular velocity of the particle is 4 radians per second. So suppose you have a particle moves in circular path with initial velocity, angular velocity, initial angular velocity, omega naught, let's call it, equals 4 radians per second. That's at t equals 0, okay? And the question is, one more. And the angular acceleration alpha is equal to 2 radians per second squared. Okay? The question is, what is the angular displacement theta at t equals 3 seconds? In other words, after 3 seconds, what's the angular displacement of that? And also, and what is the angular velocity at that time? Okay, so if I make a simple graph of this thing, imagine you have, here is a circular path, something like that, and let's say this is the y-axis, this is the x-axis, and let's suppose that at t equals 0, the particle is right here. So this is at t equals 0, and the particle angular, here we go, initial angular velocity is 4 here, okay? And the particle is moving like this. And after 3 seconds, what is the angle here? You see what I'm saying? So what is the angle after 3 seconds? So how do we do it? Well, one way to do that is to use kinematics. So what's given to us? Let's write down what's given to us. Well, it is the omega naught is equal to 4 radians per second. He wants the theta at t equals 3 seconds. The alpha angular velocity, acceleration is given to us, 2 radians per second squared. And he's looking for theta, right? So one way to do that, theta, if you go back to the kinematics, I'm going to use a third one right here. Or I can use this one. However, this one requires that I need to know omega later. You see what I'm saying? On the 3rd second. So let me start with this one right here, the third one. So the third one says theta equals omega naught t plus 1/2 alpha t squared. And everything is given to us in this. So we have 4 times 3 seconds plus 1/2 times 2 for alpha, and then 3 squared. And there we go. I will be able to find the angular displacement. So that will be 12 plus that will be 9. Is that right? And that will be, in this case, 21 radians. Okay. Now, if you don't have a feel for radian, let's convert it into degrees. So I know that 21 radian over 1 times 180 degrees over pi radian. Is that right? That will be one way to do it. Maybe you have your own way. And then when we calculate that, that will give me, let me use the calculator. I will get 12038, sorry, 0.38 degrees. Well, how many revolutions is that? I mean, one revolution, 360. So how many number of revolutions? So I go 1203.8 degrees divided by 360 degrees, because one revolution 360 degrees, and that'll be about 3.34 revolution. In other words, going back to the diagram, the particle, let me put a different color. So the particle is going to go 1, 2, 3 1/3 of the way, somewhere here. You see what I'm saying? Said 3 1/3, roughly 3.3 revolution until it stops. Okay, within that time frame of 3 seconds. You got that? Okay. All right. Good. The next topic that I want to talk about is centripetal acceleration. Change the color. Centripetal acceleration. So what is centripetal acceleration? Let me just review very quickly. So we said that if you have an object moving in a circular path, whoops, this is not a good circle. I have to be kind of pay attention until I make a circle with this stylus pen. Anyway, so if you have an object, let's say it's moving, you know, in a circular path, like in this direction. So here is the object moving, let's say, you know, counterclockwise, all right? And here is the radius of the path. So the motion of this object, so there is a velocity going this way. This is the velocity of the object. And it could be maybe accelerating, so we call that the tangential acceleration. Why we call it tangential? Because what is a tangent? Here is a circle, if you remember from geometry. Here is the tangent line. So it is in the direction of the tangent line, so we call that the tangential acceleration. And this tangential acceleration is equal to alpha r. Okay, where alpha here is the angular acceleration, and r, of course, is the radius of the circular path. All right, and of course there is also omega, which is the angular velocity, how fast the object is going around, how fast it is, making radians per unit time. Okay, and this omega and v here, omega and v are related in that v equals omega r. We talked about all of that. So those are basically the equation that we have. Now, in general, whenever you have an object that changes direction, say in a circular way, as you can see, it is constantly changing direction as it goes around. I mean, at this location right here, the object is pointing outward, upward, and this location is downward, this one is to the, say, to the right, and here to the left, and so on. So it's as it goes around in a circle, or even in a curved path, the object is constantly changing direction, as you can see. See what I'm saying? So when an object changes direction, you will have another acceleration in addition to the tangential acceleration. We refer to it as a centripetal acceleration. The word centripetal is from the Greek. It means center-seeking acceleration, or an acceleration that is pointed toward the center. Okay? So if I go back to this drawing here, and let me change my color. This centripetal acceleration will always be pointing toward the center, and we call it I think the book called it A sub C, centripetal. Some books call it A sub R for radial, because it's in the direction of the radius. Either way is fine. I'm going to stick with A sub C. Okay, and this acceleration a sub c is equal to v squared over the radius. Okay, the v squared here, basically the velocity, the linear velocity or the translational velocity v as the object is going around, divided by the radius of the path, and that will give you the centripetal acceleration. Okay, so now we're going to add this formula to our bag of formulas that we have accumulated, and then let me show you some pictures, some diagrams. Here is from the book here, the centripetal acceleration, and here is the circular path of an object like that. It's going around. And that is the velocity. As you can see, the velocity is constantly changing direction. Say this one is going down this way, this one is going up that way, and so on. And because the object is changing direction, you have this acceleration that is pointing toward the center. Okay, that's center-seeking acceleration. Here we go. All acceleration vectors point to the center of the circle, which is somewhere here. You see what I'm saying? So that's what it is. And it's equal to this acceleration, what we refer to as the centripetal acceleration. Here he goes through the derivation. But anyway, the final result of it is this one right here. This is the most important formula. The centripetal acceleration is v squared over r, and it's always pointing toward the center of that circular path. You see what I'm saying? Another way of writing it is a equals the same formula, omega squared r. Why that? Well, look, if I have, so we said that the acceleration is v squared over r, but we know that v is omega r, remember? It's right here. Right here, see it? So I can plug it in there, so the centripetal acceleration becomes omega squared r squared over r, and therefore a sub c is equal to omega squared r. So that's another version for it. It's the equivalent version, whichever you want to use, or depending on the problem that you're using. And there we go. So we have this one right here. Okay. There we go again. Here is the circular path, an object going around. The velocity is changing constantly. Here is the omega, the angular velocity. And as you can see, the acceleration is center-seeking, centripetal. Center-seeking. All right, let's do this problem here, this example. It's at 412, the acceleration of a Ferris wheel. He says a typical carnival Ferris wheel has a radius of 9 meters and rotates 4 times per minute. Okay, so what is that? That's kind of a revolution, 4 revolutions per minute. We can think of it like 4 RPM. I can think of it in terms of frequency with the funny units, right? Remember, frequency always revolution per second. So we're going to convert that to second. What speed and acceleration do the riders experience? Okay? What speed and what acceleration? What he means by that is the acceleration A, not angular acceleration, but the A, the centripetal acceleration, and the velocity given this information. All right, so let's see what we can do. So here we have a Ferris wheel, and given to us that the radius is 9 meters and rotates at a rate of 4 rev per min. Again, you can think of this like frequency. I'm going to call it F for now. And that immediately converted into revolution per second. So that's 4 divided by 60 rev per sec. Or I can just say 4 divided by 60. Let me use my calculator. So I have here 4 divided by 60. It's going to be a tiny number. That's going to be 0.0667. My handwriting is not very pretty, sorry. 0.067 revolution per second, or what, hertz, right? Okay, good. Then what is he asking for? Well, he's asking for the acceleration. He said, let's go back to the problem. He said, what speed and acceleration? So he's looking for the acceleration. He's looking also for the velocity. Okay. Now the acceleration, I think what he means is the centripetal acceleration. We know that the centripetal acceleration is v squared over r. The radius is given to us right here, so no problem. I just need to find the velocity. So I need to find the velocity first before I find the acceleration. And as I told you before, there are two ways to do that, to find the velocity. One way is the one, well, here it is. So we know that velocity is equal to omega r, remember? And omega is 2 pi f, yes? So I can plug it in there, so that v equals to 2 pi f times r. You see what I'm saying? And I think we have everything, so I just go 2 pi, f is right there. So I have here 0.067 times 9. And then when I plug all of that stuff in, so that times 6.28 times 9 equals to 3.77 meters per second. Now, if you go back to your notes from the beginning of this lecture, we said that there is another formula. There's another method, that is, or velocity equal what? Circumference over time. Remember that? Circumference divided by time, or the period. Or in mathematically speaking, 2 pi r over tau. Remember that? We talked about it. So we can do this one as well. So let me use this, and hopefully we'll get the same answer, of course. So what is tau? Well, tau is the reciprocal of the frequency. So that's 1 over 0.067. So tau in this case is equal to 0.067. And then the inverse equals 15, I would say, about 15. So that's 15 seconds. There we go. That's the period. And therefore the velocity, so here's the velocity right here. So the velocity is 2 pi times r is 9 divided by 15, and we should get the same answer. So that's going to be 9 times 6.28 divided by 15. Answer 3.77 meters per second. And there we go. Okay, you got it? Okay, so now we have the velocity using two methods. Now he wants the acceleration. That's easy. So just v squared over r. It's just simply plug in the number that we got, 3.77 quantity squared, divided by the radius, which is 9. And then we would calculate that. And I got 1.6 meters per second squared. And there we go. I got the centripetal acceleration of this object. Okay. Okay. One more example from the book. I want to look up example 4.14. This is the topic of non-uniform circular motion. Basically the kinematic equations, rotational kinematic and translational kinematics, or the book calls it linear kinematics, same thing. Remember that? So let's do one more problem. There we go, this one here, example 414, slowing fan. He said a ceiling fan spinning at 60 RPM, 60 revolution per minute, coast to a stop 25 seconds after being turned off. Okay, so it takes it 25 seconds to stop the moment you shut it off, right? How many revolutions does it make while stopping? Got it? So it is decelerating, and while it is stopping, how many revolutions does it make? All right? Interesting problem, I hope. So let's see. So we have a fan. It's slowing down, of course. And he said that the frequency of the fan, which means how many revolutions the fan makes, he said 60 RPM, which is rev per min. Got it? I can convert it immediately. Again, always convert to hertz, revolution per second. So it is 60 divided by 60 rev per sec. So that basically, excuse me, 1 hertz. Is that okay? This is what's given to us. What else is given to us? Sorry. Stops. Okay, after 25 seconds, it turn off. So it stops. So after 25 seconds. So the time here is 25 seconds. And he said, how many revolutions? Now, when he asks you for the number of revolutions like that, he's really asking you for the value of theta in radians, and then you convert the radians into revolution. You got that? So always, whenever you're being asked to find how many how many revolutions have been done, how many rotations, how many cycles, and so on, he's really asking you for the value of theta. Okay, and then you can convert theta into degrees or radians. You know, okay, or revolutions rather. So he's asking really for theta, like that. Okay, so we can use kinematic equations, given that he gives us the time. I'm looking for theta, so I'm going to go to the third kinematic equation. Let me show it to you in the book, the one I had it in my notes as well, right here. He had it at number 2, right here. Okay, so that's the one we're going to be using. Or let me show it to you from the notes here, right there. The one I want is the third one, right here. Theta equals omega naught t plus 1/2 alpha t squared. Okay. Now I could easily use this one as well. You see what I'm saying? It really doesn't matter. I can use either of them, but there is something else. There is a little catch here. Let me just elaborate. So the formula that I'm going to use is, let's say I want to use the third one. So theta equals omega naught t plus 1/2 alpha t squared. That's the equation I'm going to use. Now, if you look at it, what's missing from this equation? While you're thinking about it, let me write down the other two rotational kinematic equations. The first one is omega equals omega naught plus alpha t, and the second one, omega squared equals omega naught squared plus 2 alpha theta, right? Those are the other two. All right. So what's missing here? He wants theta. The initial omega, I can find it because this is really the initial frequency right here, if you know what I mean. So I can get that because I know that omega naught is equal to 2 pi f naught. Remember that? So I can easily find omega naught, no problem. T here is 25 seconds right there, no problem. Now I have the alpha that I don't know. You see what I'm saying? So I need to find alpha before I can use this equation. Okay? So how do I do it? Well, let's look at the other. So when you get stuck like that, you look at the other kinematic equation and hope that one of them will allow you to find whatever you're looking for. You see what I'm saying? So I'm going to appeal to the first kinematic right here. Would I be able to use this one and find alpha? And the answer is yes, because the final angular velocity of the fan is 0, because it stopped after 25 seconds, remember? So omega here is 0. Omega naught is this one. I can get that number, no problem. And t is 25, so I can easily find alpha. You get that? Once I find alpha, plug it in there, and I got theta, and I'm done with the problem. You see the plan? Okay. So let me get omega naught first, the one above me here. That's going to be 2 pi. F naught is 1 hertz. So that would be 2 pi times, well, it'll be 6.28. 6.28 radian per second, okay? This is the initial angular velocity of the fan. You see what I'm saying? Now, the final angular velocity of the fan, the final angular velocity is 0, right? Stopped. Okay. So now I come to the first kinematic, rotational kinematic. This one is 0. So therefore, alpha is equal to minus omega naught over t. I like this minus sign. Why do I like it? Because the angular acceleration is a negative. It's a deceleration. And when you have a deceleration, that means you're going to get a negative sign. And there we go. The mathematics takes care of itself automatically. and give me that minus sign. And you want to keep that minus sign. So it's going to be minus omega naught, which is basically minus this number. So that's minus 6.28 divided by T. T here is 25. So this will give me the value of alpha, and that's equal to negative 0.25 radians per second squared. There we go. I have the angular acceleration. Okay. Once I got that, I need to use this equation right here. Oh, you know what? You can use this one. It doesn't really matter. You know what I mean? I can use either this one or this one. It will give me the same answer. I'm going to use this one, and you go ahead and try that and see if you get the same answer. I'm sure you will. So let's use it. So we have here theta equals omega naught t plus 1/2 alpha t squared. And then I can just plug in everything. Omega naught, I got it to be 6.28. The time is 25 seconds plus half times, put that minus sign, be careful, 0.25. You want to put that minus sign times 25 squared. And then we calculate all that. And when I calculated, I get, I hope you calculate with me, I get 78.9. I hope I got it right. Radians. Here we go. This is the number of revolution. Now, I would like to know it in terms of how many revolutions. This is radians. How many revolutions? Well, I know that 1 rev is what? 360 degrees or 2 pi radian. You see what I'm saying? So 2 pi radian is 1 revolution. So I can simply take this and divide it by 2 pi, which is 6.28. See what I'm saying? So now the number of revolution is theta 78.9 radians divided by 6.28 radians. So how many revolutions does it make until it stops? I'm going to divide that. I will get 13 revolutions. And there we go. That's kind of a neat little problem. I hope you learned something from it. Okay, one more problem. Problem number 65 of the textbook. Let me go there very quickly. Textbook 65. I'm going to do only the first part. You can do the second part. The second part is not that bad. There it is right here. Level 3 is supposed to be challenge or difficult. I don't find it difficult. Anyway, let's see what it is. It says a typical laboratory centrifuge rotates at 4,000 RPM. Okay. So you have a lab, for blood samples and stuff. You find them in the hospital, those small centrifuges. So it spins at a rate of 4,000 revolutions per minute. Test tubes have to be placed in a centrifuge very carefully because of the very large acceleration. All right. Part A says, what is the acceleration at the end of the test tube that is 10 centimeters from the axis of rotation? Okay. Kind of a simple problem, I hope. B, for comparison, what is the magnitude of the acceleration a test tube would experience if dropped from a height of 1 meter and stopped in 1 millisecond long encounter with the hard floor? I don't think I want to do this problem. It's not related to what we're doing. I'm just going to do the first part here. Okay? So let's write down what's given to us, and then we'll try to solve it. It's not a difficult problem, I hope. I usually discuss this particular problem in class, both of them, part A and part B. Anyway, so what's given to us is that you have a test tube and the frequency is 4,000 RPM, rev per min. Let me convert that quickly. Again, make it a habit. Just convert it very quickly. So let's have here 4,000 divided by 60, and that gives me 66.7 hertz. Okay, so that's the frequency right there. All right. So how does it look like? Well, it looks something like this. You have the test tube is something like that, and it's anchored here, if you know what I mean, and then it rotates like this. If I can draw that like this, okay? And then the say the blood sample or whatever is right here, okay? And so it has that circular path to it, and this is the velocity, if I can do it vertically. Something like that. That's the velocity right there. Okay. And the radius is, he said, 10 centimeters. Is that right? Let me go back. Typical tube is placed. What's the acceleration at the end of the tube? 10 centimeters from the axis. Okay. So that's basically what it is, right? Another drawing would be, here is the circular path. Here is the center. And here is the test tube right here. Something like that, and it's going, there we go, this is probably a better picture. This is velocity, this is the radius, and it's spinning, you know, at 4,000 revolution per minute, okay, or 66, roughly 67 revolution in 1 second. That's really fast, you could hardly see it, okay? So that's basically what's going on. So how do we do it? Well, he wants, what is the acceleration? So we know that the acceleration is v squared over r. He's asking for the centripetal acceleration. And I need to find v. Again, you can find v with two different ways. Omega r, which is 2 pi f r. Now we get one formula to find v. Or the other one, the book's favorite, is 2 pi r, the circumference over the period. Either way, you're going to get the answer. Okay, I'm going to use this one right here. Okay, so what's going to happen is if I take, let's say I want to solve it symbolically first, which means I'm not going to put any numbers first. So I'm going to take that and plug it in here. So that means the centripetal acceleration, A sub c, is equal to v squared, which is basically 4, this is v squared, so 4 pi squared f squared r squared over r. This and this r cancel out. So A sub c is 4 pi squared f squared times r. And there we go. That's an expression for the centripetal acceleration. Okay. Plug it in. Plug in all the numbers. 4 pi pi squared times f squared is right here, guys. 66.7. So that would be 66.7 squared times the radius. He said is 10 centimeters, which makes it 0.1 meter, right? And then we can just calculate that. Go ahead and calculate it with me. So I got 3.14 times 4 times 66.7 times 0.1. If I did it right, I got 1.75 times 10 to the 4 meters per second. Is that a large acceleration? That's a huge acceleration if you see it. That's the reason why they put it in such a high angular velocity or high frequency of 4,000 RPM. The reason is because you want to attain a huge acceleration to separate whatever inside the sample here. You see what I'm saying? So anyway, there we go. That's the answer. Okay, let me move on to the next topic, which is dynamics. How do we include forces into those kinematic variables that we have been dealing with? You see what I'm saying? All right. Dynamics of circular motion. So what does that mean? Well, imagine you have a stone, okay, and you fasten it to a string, and then let's say you whirl it above your head, okay. So a top picture would look something like that, a top view of it. Here is the circular path of the stone as you whirl it around, right? And here is where your hand is, and here is the string, and here is the stone here, right? And let's suppose it's going in this direction. So what's happening is that you are pulling on the string toward the center like this. And as a result of that, the stone would move in the tangential, in a circular way, where this is the tangential velocity v, okay? So you're pulling on it with the force F here. We call it the centripetal force because it is, again, just like the centripetal acceleration, it's toward the center, okay? So you're pulling on the string toward the center. As a result of that, the stone, you're pulling on the string toward the center. As a result of that, the stone would move in a circular path like that, okay? And this is the tangential velocity. So we have here the forces, the sum of the forces is equal to ma, but this a is special. It is the centripetal acceleration, okay? And the sum of the forces for this case would be this centripetal force F, and if a sub c would be equal to the centripetal acceleration, which is m v squared over r. Supposedly r is the radius of the path, okay? R. And so there we go. This is basically the equation that governs such motion. I'll give you an example. I'm going to give you a bunch of examples. Let's start with a car. Let's say you are driving your car and you are turning on a level ground. So here is a top view. I think this is an example in the book. Let me look it up very quickly. Example 8.3. Oh, there it is, right here. That was good. Okay, it says turning the corner. What is the maximum speed with which a 1,500 kilogram car, that would be a small car, such as, say, a Honda Civic or something like that. So 1,500 kilogram car can make a left turn around a curve of radius 50 meters on a level unbanked road without slipping. So here is the car, okay? The mass of the car is 1,500, and this is the left turn right there. So the car is moving like this. This is the tangential velocity, v. And of course, since it's going in a circular way like that, there will be a centripetal acceleration toward the center. You got that? And here's the data that is given to us. So he said, what would be the maximum speed that the car would go around the curve without slipping? Of course, if the car is going really fast, it may go, rather than going like that, it will go, it will go in the radial direction outward, okay? So what would be the maximum speed? Well, the maximum speed depends on the friction force, or the coefficient of friction, okay? So let's work out this problem. So I'm going to make my own diagram. So here is a top view of the whole situation. Here is the circular path that the car is making. Here is the car right here, all right? And here is the radius of the circular path, supposedly r. The velocity v is like that. And the centripetal force is going to be toward the center. Got it? Now, this centripetal force is basically the friction force. See, if there was no friction toward the center, the car is not going to be able to negotiate a curve like that. So what's happening is that the friction force is in this direction, and that friction force F will play the role of the centripetal force. You got that? Remember, the centripetal force, there is no expression for it. It is other forces that take the form of a centripetal force. For this matter, it is the friction force. So going back to this equation right here, or this one, so Newton's second law, that is. So we have here sum of the forces is equal to ma, a sub c, that is. The sum of the forces here, we only have one force in this radial direction, so that will be the friction force equals mv squared over r, okay? Now he's asking the question, what is the maximum? Find the maximum velocity that the car could go around without slipping. You got it? Okay, so I'm going to draw another picture, and the other picture is basically, imagine that, so this diagram basically a top view of the car going around. Imagine that you are standing somewhere on the road here, for example, looking at the car coming towards you. How would that look like? Well, here is the car. Let me draw another diagram. So here's the car. These are the light, headlights. Here's the car right here. Here is the steering wheel. Here is the driver. And these are the wheels, the tires. Something like that. Here is the road right there, okay? And it's not the best, isn't it? That's a long wheel. But anyway, you got the idea, right? So now I ask the question, what are the forces on the car as it is heading towards me? Imagine that I'm standing right here somewhere. And the direction of motion, of course, is this way. Well, there will be the weight of the car right there. And then we have the normal, right? These are all vertical vectors. I'm unable to do it. But those are the two, right? Of course, there is no motion in the vertical direction, so therefore, sum of the forces in the y direction, in this case, equals 0, not ma. There is no motion in the vertical direction. So we have here n minus mg equals 0, so therefore the normal is equal to mg. Nothing surprising here, I hope, okay? So we have that. So back to my equation right here, this one. So we said that the friction force is equal to mv squared over r. The friction by definition is mu n equals mv squared over r. And n, what is n equal to? Well, we just proved it to be equal to mg according to this derivation. So therefore, mu mg equals mv squared over r. The masses cancel out, so I have mu g equals v squared over r. So he said, what is the maximum velocity, correct? He said, what is the maximum velocity? Well, v max happens when mu, the coefficient of friction, okay, is max. Well, when is it max? Well, if you remember, it is the coefficient of static friction. In other words, if mu sub s is almost equal to, if you look up the table, you have to look up the table for that, and that's equal to almost 1. It's something like 0.98 or something like that. But again, I got this information from the book, from the table, not a derivation. Here we go. So he said mu sub s is equal to 1. Again, that's according to the table. You have to look up the table for that. So this is just a number. So so the maximum velocity happened when the coefficient of friction is maximum. Okay. So I'm going to put an S here, which is the static friction, and therefore solving for V max, that is, and that's going to be R mu S times G, all of that under the square root, and there we go. We are pretty much done with the problem. All I need to do now is just plug in my numbers. He says, going back to the problem, he said the radius is 50, the mass is 1500, right? And of course, mu is 1. So we have here, the radius is 50, 1 for the coefficient of static friction, and G is 9.8. And then we calculate that to be equal to 22 meters per second. Okay? And that's probably a realistic number. 22 meters per second is about, give or take, probably 44, 45 miles an hour. So that's about 45 miles an hour. So imagine that you're going around the curve with 45 miles an hour, unbanked, okay, on level floor. So that would be anything above that will probably cause you to slip. So that's basically the story of this problem. All right, another problem. I have a bunch of them here. I'm looking at problem number 8 from the book. So let me go up to the, that's not an example, that's from homework. Number 8 right there. There we go. It says the Bohr model of the hydrogen atom, an electron of mass 9.1 times 10 to the negative 31, orbits a proton at a distance of 5.3 times 10 to the negative 11. This is called the Bohr radius. The proton pulls the electron with a force, electric force, actually electrostatic force, equal to 8.2 times 10 to the negative 8 Newton. Okay, how many revolutions per second does the electron have? Okay, very interesting problem. All right, let's see what we do. So the Bohr model basically, it's similar to a solar system model. What Bohr says is that the electron orbits the proton in the hydrogen atom. The hydrogen atom, if you remember, the nucleus only has one proton. There are no neutrons, and there is only one electron. It's a very simple atom. 75% of the universe is basically hydrogen. So anyway, so here's the proton right here, and here is the electron. Suppose the electron is moving in this direction like that, say counterclockwise. And this is what we call the Bohr radius. Okay, so this is the proton right here. I'm going to call it P. This is the electron, E. This is the Bohr radius. I'm going to call it R naught. This is what it's called in the literature, in nuclear atomic physics literature. And it's given to us. It says R naught is equal to, it's right here, 5.3 negative 11. So it's equal to 5.3 times 10 to the negative 11 meters. Okay. And then he says that the fundamental charge, or the charge on the electron, it's called, I'm sorry, we're not doing the charge. I'm sorry, I'm talking about the mass. The mass of the electron is 9.11 times 10 to the negative 31 kilogram. That's the number I've always memorized. That's the mass of the electron. Okay. So as the electron is moving about the proton like that, all right. So let me make another drawing just to put for the forces. So here is the circular path. Here is the electron. Here is the proton right here. Here is the electron. Here is the Bohr radius. So as it is moving, there is the velocity right here, which is tangential. Here is the centripetal force, F sub c, right? Centripetal force. Remember, like I said, there is no specific expression for the centripetal force. Other forces, other real forces, take the form of the centripetal. Just like in the previous problem, it's the friction force that acts like a centripetal force. Here, however, it says in the problem right there, it's the electrostatic force. He said, the proton pulls the electron with an electric force of this amount. So this is what is called Coulombic force, the force of Coulomb. That's the force that is taking the role, or playing the role, of the centripetal force. You got that? Okay. So I'm going to call it F for now, or F sub c. So now, again, using the second law of Newton, sum of the forces equals ma sub c. So here I have F sub c, that's the only force I know, which is that number, we're going to put it in there. The mass of the electron times v squared over the Bohr radius. Got it? V squared over r. You know, A sub c is v squared over r. Okay. And that's about it. He's asking for what? I forgot what he's asking for. How many revolutions? All right. So what I want to do here, I got pretty much everything except the velocity. I have the Bohr radius right here. I have the mass, and I have the F sub c is given to me. So I can find the velocity. So let's do that. So I have here solving for the velocity. V is equal to, this case, the Bohr radius times F sub c over m sub e, all of that under the square root, right? And then we plug in the numbers. So I have here the Bohr radius 5.3 times 10 to the negative 11 times the centripetal force is right there, 8.2 negative 8. 8.2 times 10 to the negative 8. All of that divided by the mass of the electron, 9.11 times 10 to the negative 31 kilogram. And all of that is under the root. I just put it to the power of half. Let me get this number very quickly, and please calculate that with me. Make sure I'm not making any stupid mistakes here. So I have here 8.2 E negative 8, whoops, 8.2 E negative 8 times 5.3 E negative 11 divided by 9.11 E negative 31. All of that under the square root. My answer is 2.18 times 10 to the power of 6. I hope I did it right. Meters per second. There we go. So this is the velocity of the electron around the proton. Can you believe that? Almost 2 million meters per second. Extremely fast. It's not surprising. All right. So he says number of revolutions. So he's asking for, let me read the problem again. The last one. How many revolutions per second? What is he asking for? He's asking for the frequency. Remember the frequency? It's number of revolutions per second. And frequency is related to angular velocity, omega, right? Omega equals 2 pi f. And velocity v is related to omega. So let's take it slowly. So we have here, he's asking for frequency f, and we know that omega is equal to 2 pi f, correct? We also know that v equals omega r. So I already know v right here. So I can find omega, and from omega I can find f. From omega I can find f. Or I can do it all in one shot. Look at this. So I have v equals omega r. Well, omega is 2 pi f, so that's going to be 2 pi f. 2 pi f r. And so I can solve for f. So f will be, in this case, v over 2 pi times r. There we go. This is what he's looking for. And he wanted specifically, he said, what is how many revolutions per second? All right. So everything is ready to go. So we can just plug in the numbers into this equation. So the velocity, again, I'm plugging things into this one. So the velocity is going to be equal to 2.18 times 10 to the 6. I hope I did this right. I don't have the answer in front of me. 2 pi times r is the Bohr radius. 5, put a little knot here maybe, because it's a Bohr radius. So 5.3 times 10 to the negative 11. And then now we can get how many revolutions the electron would be able to make. So let's do it. 2.18 E6 divided by 2 divided by 3.14 and divided by 5.3 E negative 11. My answer is 6.8 5 times 10 to the power of 15 revolution per second, or hertz, if you will. You see what I'm saying? What does that mean? It means the electron in this atom right here goes around the proton. How many times? 6.5 times 10 to the 15 times per second. If you can even imagine that, if you can, comprehend something like this. But anyway, that's what it is. And I think it's the correct number. I have the answer in the back, in front of me, on the back. Okay, great. One more problem. I want to do number. I have a hard copy of the book in front of me. Number 13 from the problems. Right here. It says here, so you look at this table right here. You have a table or a surface. There is a hole right here. Okay, let me make it. There we go. So you have think of it like a table or a surface. There is a hole right here. There is a string that goes through the hole, and then one end of the string down here, you put a mass. We're going to call it M2. I think M2 is larger than M1. And then the other side, you put a mass M1. This looks like a puck, hockey puck. So as M2 comes down, the hockey puck would go around in a circle like that. Okay? Something like that. I think we are assuming that the radius here is a constant. If you want to do a tougher problem, that this radius is actually decreasing. But anyway, so I think this is what the problem is. Let's look at it. He says, as we read, look at the diagram here. He said mass M1, which is the top right here, on a frictionless table, is connected by a string through a hole in the table hanging M2. With what speed M1 rotate? With what speed must M1 rotate in a circle of radius R if M2 is to remain hanging at rest? So in other words, see if it's coming down, if M2 is coming down, what's going to happen? The radius here would be decreasing. And as it is decreasing, the speed of this puck is going to go faster and faster. It becomes a more complicated problem. It requires a little bit more sophisticated formulation to solve it. We're not doing that. We're just saying that if M1 is moving in a certain velocity in such a way that it will keep M2 from not descending down. Okay? He's asking, what is that velocity? Let me read the question again. With what speed must M1 rotate in a circle of radius R if M2 is to remain hanging at rest? Got it? Okay. So let's do that. Nope, that's a problem. Okay, so let me draw the diagram. This this picture right here. Let me put it on the side so you can see it within the frame. Yeah, okay. So it looks something like that. Here is the table. This is a famous problem. You find it in just about any physics book. Here is a circular path, something like that. Here is the hole right here. And out of the hole, you get this, the puck, what I call the puck right here. And then it runs down. And then you have the other mass M2 here. Mass M2. This is mass M1, and it's moving around in a circle like that. And this is the radius is a constant, okay? So it's a symbolic problem. There's no numbers there. So how do we solve something like that? Again, I'm going to draw this in a free body diagram. basically put forces. So here is the hole right here, right? I'm going to draw, rather than drawing the mass here, I'm going to put it right here. You know what I mean? Let me put it in a different color just to show what I'm talking about. I'll put a pink. Imagine the mass is here. Remember, it's going around, right? So imagine the mass at this instant of time is right here. So in this case, again, I'm doing that just to make things simple. So we will have, here is the mass right here, the top mass, the hockey mass, you know, the hockey puck. And here is the mass M2 like that. You get that? I hope everyone is able to picture what I'm trying to do here. And now we ask the question, what are the forces on each? Well, this mass right here has a tension. Remember, this is the hole right here. There's a tension, we're going to call that T. Remember, tension is always out of the body. And then we have that same tension is out there. We discussed all of that when we were doing pulley problems, previous lecture. And that is the weight M2G. Okay? So here, the tension, T, this one, okay, it plays the role of the centripetal force, or rather the centrifugal force, if you will. You see what I'm saying? It plays the role of the centrifugal force. So here we have some of the forces. Sum of the forces F equals ma. Now the object that is rotating is the m1, not m2. So I'm gonna, that's because, you know, m1 here, the mass here is the rotating object. It's always the rotating object. So it is m1 in this case, right? All right. So in this case, we would have the force T equals m1 v squared over r. All right. He said, with what speed? So we're looking for that speed, v. Now, before I move any further, let me go to m2 right here. Right here, guys. Okay. So I got this from here, from this part. Now this one, I have here what? Remember, the M2 is not moving, so that means T minus M2G equals 0. So therefore, the tension is equal to M2G. So I can take that and put it over there. So I have here M2G equals M1 V squared over R. And then I'm going to solve for the velocity. So velocity in this case is going to be equal to M2 over M1 R times G. All of that under the square root. Okay. And there we go. That's it. There is no numbers to plug in. He said, let me go back to the problem. He says, with what speed must M1 rotate in a circle of radius r if M2 to remain hanging? Well, there it is. This is the speed. You know, put whatever numbers you have for M2 and M1. It's not given to us. And that's about it. Okay, good. One more problem, I'll do number 16. Right here. Okay, it says a 9.4 times 10 to the 21 kilogram. Before I read anything, that looks like a planetary object, because this is a very large mass, 10 to the 21. Okay, so we have 9.4 times 10 to the 21 kilogram moon orbits a distant planet in a circular orbit of radius 1.5 times 10 to the 8 meters. it experiences 1.1 times 10 to the 19 Newton gravitational pull. So what is that? This is the centripetal force. You know, it takes the form of the centripetal force. So gravitational pull from the planet. What is the moon's orbital period in Earth's day? So basically he wants tau, okay? He wants tau, the period. What is tau? Well, if I know the frequency, it's the reciprocal of the frequency. And how do I get the frequency? If I know omega. And how do I get omega? If I get V. You see the plan? So that's basically how you do it. All right. So again, I'm going to draw a picture of this. So it looks something like this. Here is the moon right here. Well, first of all, let me draw the orbit. Here is the orbit of the moon. Here is the moon right here. And here is the parent planet right here. Let's make it this big. Okay, this parent planet is big M. I'm going to call it big M. Remember, this is the planet. That's the moon of that planet, and it's going around in this direction, for example. Like that, okay? This is the radius, and then there is the gravitational pull, F. Okay, and F here is given to us. Again, the F here will play the role of the centripetal force. Okay, this is like the third or fourth time we see the same thing. So it plays the role of the centripetal force, and it's equal to this number, 1.1 negative 19 right there. Okay, the radius R here, the radius is 1.5 to the 8 meters, and the mass M of the moon, the orbiting object, is given also to us right there. So simply use the same formula, sigma F equals ma. A here is C, and this is C. So basically the force F equals to the mass of the moon, V squared over R. Okay? And I'm solving for V, so that's going to be RF over M, all of that under the square root. Okay? And once I do that, okay, I'm going to plug in the numbers. Once I do it, I get V. Then what's the next step? Remember, he's asking for what? 16. He's asking for what is the moon's orbital period, okay? So what he's asking for is tau. Correct? So let's do it. So from this formula, I will get V. And then I'm going to go, well, V equals omega R, so I can get omega, right? In this case. And then from omega, I can get what? I can get F, because omega equals 2 pi F. Whoops. 2 pi F. And then from 2 pi F, I know that I will get F. And from F, I know F is equal to 1 over tau. So I'll be able to get tau, and that's what he wants. You see the plan? So let's do it quickly. So I have here the velocity V is equal to, R is given to us 1.5 times 10 to the 8 times the force, which is 1.119. All of that divided by the mass of the moon, which is 9.421. All of that to the power of 1/2, or the square root. And let's calculate that. Please calculate with me. So we have here, my calculator is not working for some reason. I should have another one somewhere. Okay, so I have here 1.119 times 1.58 divided by 9.421. All of that under the root. And if I did it correctly, the velocity is 419 meters per second. Okay, there we go. So I got the velocity. I think it's a reasonable number. Now I get, let's look at the plan right here. With V, I'm going to get omega. So omega is equal to V over R. So let's get that. So that's 419 divided by the radius. It's equal to 1.5 times 10 to the 8. So let me get that. So that would be divided by 1.5, 8, answer 2.7, let's say 2.8 times 10 to the power of negative 6 radians per second. Okay, let me box it. I like to box my answers. That's a very good idea to do that. Okay, and then again, go back to this. From omega, I can get F. Or if you want, I mean, there is a quick way of doing it. Let me show you. See, omega is 2 pi F, but F is 1 over tau, so it's 2 pi over tau. That'll be one shortcut. So therefore, tau is 2 pi over omega. So we can do that in one shot. So I have 2 pi divided by omega, which is 2.8 times 10 to the negative 6. So let's do that. So I have this answer. I get this big number, 2248396.3 second. All right, doesn't look like a pretty number. He says, what does he say? What's the moon's orbital period in Earth days? All right, so here is the ugly number. This looks like a credit card number in second, which is something we cannot read very well. But I know that. How many seconds in a day? Well, 1 day equals 24 hours equals 24 times 60 times 60 seconds. Make sense? So I'm going to get this number. So 3,600 times 24. So it is 86400. 86400 second in a day. Okay? So now I can, from this information, I can find tau, the period in Earth days, by simply dividing this number over this number. So let me do that. So I have here 2248396.3 divided by 86400, and that's equal to 26 days. In other words, the moon, this moon, just like, similar to our moon, it can go around its parent planet in 26 days. Ours goes around, what, in 28, 29, and so on. Got it? That's it? Okay, good. One more problem and I will finish this video. Number 47 in the book. This one is a little bit toughy. It comes with a picture right here. Is that, no, this one right here. This is the picture right here. Here it is if you want to pause the video and draw it. So what you have, this is called a circular pendulum. It goes around in a circle. Here's the bob. Here's the pivot right here. And then it goes around like that. Okay? The length of the string is L, and this is the radius of the orbit. Excuse me, the radius of the circular path, right? All right, so what did it say? He says a conical pendulum, they call it circular pendulum or conical because it looks like it takes the shape of a cone. But I think circular pendulum is more common. Anyway, so a conical pendulum is formed by attaching a ball of mass M to a string of length L, then allowing the ball to move in a horizontal circle of radius R. The figure shows the string, blah, blah, blah. Okay, so those are the questions. He said, A, find the expression for the tension of the string. B, find an expression for the ball's angular velocity, speed, omega. And C, what are the tension and angular velocity for, and so on. So I'm going to do A and B. The C, basically just plug in the numbers of the whatever expression you get for A and B. You see what I'm saying? So how do we do this problem? Well, let's see. I'm going to put this on the side so you can see it. Okay, so the picture looks something like this. Let me draw it. So here is the, let's see, how do I do this? Start with a circular, kind of hard to draw. And then here is the cone. There we go, that's good enough. And here's the ball, I'll make it bigger. And here's the radius right here. Okay, that's the length, this is the pivot right here. The direction of the ball, it doesn't really matter, I'll just put it like that. And this is the length L. And he didn't show you this, but see, if you look at the apex of the cone right here, this is called the apex, A-P-E-X, there is an angle to the pendulum. See what I'm saying? So I'm going to put that angle because I find it important. I'll show you in a second why. So here is an angle, if I can draw that thing. Something like that. There we go. Okay. And this is the radius. All right. There we go. Now, wish I could do that in a straight line. Anyway, so what we have, if I look at this triangle right here, guys, right here, okay? I want to do some, I'm thinking about geometry for the moment right now. I'll do the physics in a minute. Because I don't have an expression for the radius. But see, he gives me L. And I know this is called, this is the theta. And this is the radius right here. So you would agree with me if you do the basic trigonometry, L, or R rather, equals to L sine theta. Make sense? So sine theta, let me write it this way, sine theta equals R over L. Let me box this one. I don't know if I need it or not. I'm just kind of trying to solve this problem, just to kind of put in all my all the ideas that I have. Another thing to keep in mind, if this is L and this is R, so what would be the length of this line right here? Well, it would be L squared minus R squared using the Pythagorean. So this is basically L squared minus R squared under the root. Make sense? So I'm going to keep it like that. Why do I say that? Well, I say that because, again, look at the triangle. You'll see that cosine theta is equal to what? Adjacent over hypotenuse. So that's going to be square root of L squared minus R squared. R squared. This R is not very pretty. There we go. Over L. Okay? So that's another expression I want to keep in mind. I'm just kind of putting in all the information that I can gather, that I can accumulate from the information given to me. All right, now with this in mind, let me go and use Newton's law. Now again, you need to run a film in your head and see how the pendulum bob is moving. So it's moving around in a circle like that. Now we asked the question, what are the forces on it? Well, the forces on it, let me put it in different color. I'll put it in pink. So there is a tension coming out of the string like this. That's the tension T. And of course there is the mg, the weight of the ball. And those are the only two forces that I can think of. So now I can resolve, let me resolve it in different color as well. How about green? I can resolve the tension T right here using theta. So it has two components. One component this way, again, excuse my crooked lines, and one component this way. This is the angle theta right here. So that's going to be T cosine theta. And then this one right here, the other one, is minus t sine theta. I'll put the minus sign in the equation. For now, I'm just gonna write it like this: t sine theta. Okay, there we go. And so now, back to black color. So now the sum of the forces in the y direction, okay, the y direction is this way, right? There is no motion in the y direction, so that will be 0. So what are we have two vectors here, t cosine theta minus mg equals 0. Remember, I don't know theta, it's not given to me. So I can solve for t. He's asking for it, right? He said, find the expression tension. Again, without theta, which is okay because theta is right here. I can write it in terms of what's given to me, L and R. Okay. So in this case, I would have mg over cosine theta, but what? Cosine theta is equal to that, so I can plug it in there, and I found my expression for t. So therefore, t is equal to mg, I'm going to do it in one shot, times L over the square root of L squared minus R squared. And there we go. I have an expression for the tension. Now, if you were taking this course with a math teacher, he'll tell you, oh, rationalize the root. Well, we don't do that in physics. And there we go. Got it? Okay, so that's part A of the problem. Part B, he says, find an expression for the ball's angular velocity omega. Okay? Omega. Well, how do I do that? Well, let's forget about this for a sec. Let's get the forces, some of the forces in the x direction, which is basically that. Look at it now. See, the ball, excuse me, the ball is going around in a circle. So that means if it's going around the circle, there is a centripetal force, and the t sine theta plays the role of the centripetal force. Okay? So we're going to go sum of the forces in the x direction equals ma, a sub c. Sum of the forces in the x direction equals mv squared over r. Right? And f, oops, let me go back to the drawing. So f sub x right here is nothing but the centripetal force, which is this one, t sine theta. There's only force that is in this direction. So here we have t sine theta equals to mv squared over r. Again, he's asking for omega. No big deal, because v is what? Omega r. I can put it in there. So let me put it in there once and for all. So it's going to be m omega squared r squared over r. So that will be basically m omega squared r. And I have here t sine theta, right? Well, sine theta is this. So I can put it in there, and t is right here, and I can put it in there, and I'm done with the problem. Then I solve for omega, and I'm done. You see that? So that's what I'm going to be doing right now. So I'm going to plug in the value of t. Oops, I can go back, sorry. So t in this case is going to be mg L over square root of L squared minus R squared times sine theta, which is that, R over L, R over L equals to m omega squared r. Again, don't be in a hurry to do the algebra, get the answer quickly. So, take your time. So you have this, let me put a different color. I can see a lot of things are reducing. So this r and this r cancel out, this L and this L cancel out, this m and this m cancel out, and I'm basically left with the omega squared, which is really nice. So I end up with, let me just keep the color. So I have here omega squared is equal to, what is it? G over omega squared over square root of L squared minus R squared, or omega is the square root, if you will, g over square root of L squared minus R squared under the square root. Okay, and there we go. That's basically how you would do this problem. I think I'm going to stop here. I think I've done enough problems on this. I will come back and do more problem on centripetal acceleration in a future lecture when I cover gravitation. Okay, because gravitation also has to do with you know, as an you know, a planet is orbiting another planet or a star. There will always be a centripetal force involved, and that would be most of the time, or a lot of time, the gravitational force takes the role of the centripetal force. So I'm going to come back and do basic problems with the application of what we have just covered to gravitation. Okay? All right. Bye-bye.